Hi, and welcome to my talk entitled Use Falco and eBPF to Protect Your Applications. First, who am I? I'm Thomas Labarussias. I'm currently OSS and Ecosystem Advocate at sysdig, the original creator of Falco. I was SRE for over 8 years, so I know what it is to run stuff in production. I'm also contributor to Falco and the creator of falcosidekick and falcosidekick, two major components of the Falco ecosystem. And you can reach me on these social networks if you want. First, we need to define what is runtime security, what it means. Runtime security are all the tools and procedures you can put in place to secure an application, in a container or not, during its lifetime in production. It's different of what we currently do in our CI pipelines with an image scanning. It's also different from what we can do with Kiveno or OPA gatekeepers to create policies to enforce good practices in our clusters. It's totally focused on what happens when your application is serving real customers, is using real traffic. For that, for Falco, we rely on syscalls. Syscalls or system calls are basically the way your program have to ask the kernel some accesses to the resources. For example, if your application needs to create a process, access to the network, read or write into a file, your application needs to ask the kernel the access. And to ask these accesses, you use system calls. Basically, you can see the system calls as the kernel API. If you're familiar enough with the Linux ecosystem, you already know about glibc or method for Alpine. Basically, glibc is the library used by your applications to call the system calls. You can see the system calls as an API and the glibc as an SDK. So for Falco is a SynCF incubation level project. It's a cloud-native project in the SynCF landscape for securing running applications. Right now, it's the most advanced threat detection engine you can run inside Kubernetes. eBPF. eBPF for Extended Packet Filter. It's the Linux kernel feature which allows you to run a program in the kernel without any change of the code or the kernel or any load of a module like we did before. It enforces the stability and the security. It's really useful for security, for monitoring, troubleshooting. You also have to know right now the core maintainers of Falco are developing a new Falco eBPF probe. Basically, the features will be exactly the same as the current ones, but it will also use the core paradigm called compile once, run everywhere. Right now, you need to build the eBPF prod for the exact version of your kernel. In the future, since the version 5.8, you will use the same probe for any kernel. You just have to download it or build it only once, and it will run everywhere. For the eBPF, how it does the collections of events. Basically, in eBPF world, you have hooks. Hooks are endpoints, for example. You can hook basically your probe and collect events. These events can be syscalls, they can be related to file system, they can be related to network, almost anything. Even a hook is not already there by default, you can create your own. It's really convenient and really easy. To ensure the stability and the security, all the code you write for your eBPF probe will be verified by the Linux kernel. So you code your probe with everything to the hook you want to use, the data enrichment, everything. It will be checked by the kernel. If the code is approved, it will be compiled into bytecode and injected to the kernel, and it will be run inside the sandbox. The verification is there to ensure you don't have any security flaws, you don't create infinite loops, you don't create overhead and bad performances in your system. Everything is there by default, by design, to ensure stability and security. For Falco itself, the architecture is there. You have the kernel, and the eBPF probes is to collect the syscalls from the kernel. And then Falco, thanks to a rule set, will trigger alerts. If one event from the kernel, from the syscalls, matches with a rule, it will Falco will output an alert. This alert can be in standard out, a file, program, syslog, HTTP, sent to an HTTP endpoint, or gRPC. If we take a deeper look at the Falco architecture, Falco is composed of three key elements: libscap, two libraries, libscap and libsimp, and ruleset. So ruleset is basic. And libscap is in charge to the event collections, and libsimp to the data enrichment and the extractions of field. You can see we have the eBPF probe in the kernel space and Falco itself in user space. It's really important for us to, as Falco is a security component, to be as secure as possible. This is why Falco itself is running at the user space, so with less privileges. But the probe, eBPF probe, is running in kernel space. But thanks to eBPF, is secured and stable by default. So we have the first library, libscap, aka library for system captures. Libscap is a user space library. It communicates with the drivers. Basically, it reads the syscalls events from a rigged buffer if exposed by the driver. And then these events are forwarded to libsimp. Libsimp, aka library for system inspections, is in charge to receive the events from libscap and to enrich these events with machine states. Basically, if your application is running inside a container, this container is part of a pod in a Kubernetes cluster. You will have for your rules and for the alert, the container ID, container name, the pod namespace, the pod labels. All these elements will be there to create nice rules and to be able to know what is the context of the alert. It will also perform some event filtering and extract fields from these events. These fields are then used by the rules. So if we take a look at our first rule, for example, this one, terminal shell in a container, we have the name of the rule, the description for us, human beings. It will not be used by any system, and it will not be in the final output. We have the condition, we'll see it later, and an output. The output is the exact message we will get at the end. You can see some fields starting by %. This field will be automatically replaced by Falco in the output. It means at the end, in the alert, you will get a real username and not this token. Each rule comes with a priority, in this case, running. These priorities are useful for you to filter which rule you want to receive. And we also have tags. The tags are useful to understand the context of the rule, what it's supposed to detect. And you can also set Falco to just enable a subset of rules. For example, you can enable only the rules which concern the container or networks or else. So for the rules, you can use lists and macros. Lists are pretty obvious. It's just an array of items. In that situation, it's a list of possible shells you can use in your system. Remember, Falco rules are YAML files, basically. So you can override anything, and you can also append items or append rules or macros. It's really convenient, and it will allow you to reuse macros over the rules and not copy paste or duplicate code. We also have this macro, shellproc, and you see macro.name. Macro.name is a built-in field from Falco you can use in your roles. even if you are not really familiar with Falco, even if you're not familiar with Linux, syscalls or stuff, it's quite easy to understand that proc.name means the name of the process. You also have proc.id for the ID of the process, or proc.pid for the ID of the parent of the process. It's really convenient and easy to read, even if you are not a specialist. We also have this macro containers. If container.id, already a built-in field, is different from host, just means if we have something different from a hash, it means the applications or the events happened inside the container, which is obvious. And we have spawn process with a typo. And we also have event.type, obvious, and exitv and exitv are real system calls. You can see these exact names inside the kernel code base if you want. And we have event.dir. It's just to specify if we want a question to the kernel or response from the kernel. Even if the rules are really convenient and easy to read, we know it would be complicated to create new rules. This is why Falco comes with a default rule set. Right now we have almost 70 system rules, and they cover most of the techniques, tactics used by the attackers to do privilege escalation, to read or write sensitive files or directory, to uh, spawn a shell, exfiltrate data, start ransomware, that kind of patterns. For example, right now we have all these rules in 79. So we can see some of them are disabled by default. It's just because they can be noisy if you don't append the exception list with your own context. So we prefer to disable them, but they are there and you can use them. We also have tags and so. So if we take a look at the rules we just saw, the condition is a little bit different because my slide is quite old now, but basically the idea is the same. We have macros, spawn process, macros is there, container, shell proc, etc., etc., and the output with the token to replace. Everything is there. You also have tags, and if you are familiar with the meter framework, we are trying to cover as much techniques as possible, and you can find which rules is related to which technique with the tags meter, underscore, and the number after. Having alerts is nice, but we need to use them. We need to exploit these alerts. Here comes falcosidekick. Falcosidekick basically is, um, forwards the alerts from your Falco instances to your ecosystem. So you can forward the alert to a chat system, a logs system like Elasticsearch, Loki, or ours, a queue system streaming like Kafka, NATS, PubSub. You can also forward alerts to a function as a service, serverless. Falcosidekick also exposes Prometheus endpoint. It's useful if you want to do some statistics about the number of alerts and so. And for the SRE or DevSecOps or Health or SecOps, you can also trigger your on-call system with Falco. Right now, with falcosidekick. Right now we have PagerDuty, Opsgenie, and Grafana on-call. And you can also do cold storage in S3 or else. Basically, we have one Falco instance per node because it relies on the kernel and the kernels are not distributed. So we have one Falco instance per node. They can forward all their events to single single deployment of falcosidekick. You can pull falcosidekick to get metrics, and you can send all the events to Elasticsearch for data analysis or long-term storage, but only alerts with priority above critical to your on-call system. You can also add static feeds or else. Really convenient. So with Falco, we have the detection. with falcosidekick, we have the notification. If you forward this event to serverless or to a function as a service system, you can react. As long as you are able to write your own reaction, you can do whatever you need with Lambda, OpenFast, Knative, uh, Argo workflow, technologies, Google function, everything. You can, for example, you can terminate a pod. You can create a network policy to isolate a pod. You can also scale in or scale out an auto-scaling group, whatever you need, as long as you are able to write your own function. falcosidekick comes with a specific output called falcosidekick UI. And basically, it's a basic interface with statistics, with pie charts, and so to have in few minutes an overview of what has been detected by Falco in your environment. It's pretty convenient. It's not used for long-term storage or else, but at least you have a quick overview. And it's pretty convenient to use. At the beginning, Falco was only for system calls. Then we introduced a web server to collect the Kubernetes audit logs, but it came with a lot of drawbacks. So in the last year, we also introduced a plugin framework. Right now, we are able to collect syscalls thanks to eBPF, but Falco is also able to collect any kind of events you may have. So by events, we often think about logs, for example. So plugins are shared libraries used by Falco to collect and stream of events. Right now, we have plugins to collect Amazon EKS audit logs, to collect GitHub webhooks, Docker events, and even Nomad events. We developed this plugin with HashiCorp. So with eBPF, you collect the syscalls. So with eBPF and Falco, you protect your applications. With the plugins, you can, for example, the Kubernetes audit logs plugins, you are able also to protect your Kubernetes clusters. With the Amazon CloudTrail, you are able to protect and to detect suspicious behaviors at your account level. And with the GitHub plugin, you are able to detect strange situations in your CI or in your pipelines or in your repositories. It means right now with Falco, you can protect all stages from the development to the production. So the situation now of Falco is we have the eBPF for these code collections. We have the plugins for the events collections, Falco and its rule engine. And to manage the plugins and the life cycles of the plugins and of the rules, we introduced a few months ago a tool called falcoctl, Falco Kernel. Basically, it will install plugins and rules, and it will also track new versions of the rules to automatically download them and reload Falco. So your cluster, your Falco fleet will always be up to date. So another view of the architecture. Basically, same idea that behind it. And once again, the plugins are running in user space. So without any big privileges. Once again, for security purpose. Time for a demo. So in this demo cluster, I have two nodes. And like I said, Falco relies on kernel. So two nodes means two Falco pods. And basically, they are deployed as a daemon set to have one Falco per node. It's quite obvious. I also installed falcosidekick UI, the front end, and falcosidekick UI. The storage backend is a Redis. And another deployment of Falco with the EKS plugin. So imagine you have this pod is your critical application. It can be WordPress, a Drupal, anything you can run and expose to internet. So an attacker gain access to this Docker, to this container. As you can see, when I created my shell, it has been detected immediately. So we have the priority, we have the exact output message with the user, root, the namespace, default, the pod name, even the container ID, and what shell has been used and what command line has been used to start the shell. All these elements are there also as output fields. They are used by Falco, falcosidekick for routing. So now I will add curl. You can see it's automatically detected in real time, once again, thanks to eBPF. So right now it's an error with packet management process launch in a container, and once again, the user, the exact command that has been run, and the container name is there, the image, everything. So we'll try to reach the Kubernetes API now. Thankfully, in that situation, the API is protected, but at least we have detected it. An expected connection to Kubernetes API server from a container. And we have the exact command. Once again, the namespace and the pod name. And now, imagine I'm overriding a critical file. Here, file below /etc has been opened for writing. And we have, once again, all elements, container name, image, and the pod. And if we take a look, falcosidekick, so we have all things that happened in the last 5 minutes, 15 minutes. We have the pie charts, statistics about the priority, the tags, the source. We can filter the source. We see what I did. And if we want more details, there. Right now, we also have terminal shell in a container. It's exactly what we saw in the logs, but in a more formatted and nicer way with the tags. We can filter, for example, on the namespace. Then we have the installation of curl, the attempt to reach Kubernetes API, and the override of the file. Everything is there. And we also have, thanks to the Kubernetes audit logs, we have the details about someone attached or execute something, executed something into a pod. We have all these details. In a real world, it will be a web shell or else, but in my example, like I did an exec, we can detect it. And once again, we have the target name, the pod name, the namespace, and so on. If you want to start with Falco, the easiest way to install and start with Falco is to use the official Helm chart. By setting these values, you will install Falco, falcosidekick, falcosidekick UI, and use the eBPF prompt in the namespace called Falco. In less than 2 minutes, everything will be set on and running, and you will be able to access to the web UI with a port forward. If you want to contribute or know more about Falco, you can join us in our Falco Slack channel, where you can take a look at our new website. A total revamp has been made in the last month, so we hope it's better for everybody. And we also on GitHub or else. Thank you and have a good day.